Proxima Centauri, the closest star to our nearby planet group, has for some time been a subject of interest for cosmologists. This little red diminutive person, found in 1915 by Scottish stargazer Robert Innes, is essential for the Alpha Centauri framework, which likewise incorporates Alpha Centauri A and B regardless of its vicinity. Simply 4.24 light-years away, it stays undetectable to the naked eye because of its relatively low brilliance. Anyway, Proxima Centauri holds tremendous logical worth, particularly as the host star of Proxima B, an exoplanet that circles within the star's livable zone. Red diminutive people like Proxima Centauri are more modest, cooler, and fundamentally longer-lived than stars like our Sun. Their low glow makes them hard to notice, but it also implies that their tenable zones are much closer to the star. For Proxima B, this means an orbital distance of 0.05 galactic units, a simple fraction of the distance between Earth and the Sun. This nearness opens Proxima B to extreme solar activity, including regular solar flares and elevated degrees of radiation, making its current environment distinctly different from Earth's. The discovery of Proxima B was an exceptional accomplishment in exoplanet research. Utilizing the radial velocity technique, cosmologists recognized subtle wobbles in Proxima Centauri's position caused by the gravitational pull of a circling planet. These wobbles allowed researchers to measure the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the presence of Proxima B, marking a breakthrough in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima B, they come with significant limitations. Atmospheric distortion and light interference frustrate Earth-based telescopes from capturing detailed data about the planet's surface or atmosphere. Most of the data we have, such as its mass, distance from the star, and orbital characteristics, is based on indirect measurements. To uncover more about Proxima B's environment and its potential for life, advanced observational instruments like the James Webb Space Telescope, JWST, are essential. The role of JWST in exoplanet investigation and Proxima Centauri's importance as a gateway to understanding exoplanetary systems couldn't be more significant. As the nearest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, specifically, presents a fascinating opportunity. A rocky, Earth-sized planet with the potential to harbor water and possibly life. However, the challenges posed by its harsh environment make it a complex puzzle for researchers to solve. The James Webb Space Telescope, JWST, isn't just another tool in cosmology. It is a revolution designed as the successor to the Hubble Space Telescope. JWST was conceived to overcome the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided invaluable insights into the universe, including determining its age and discovering thousands of galaxies, its capabilities are confined to visible and ultraviolet light. JWST, by contrast, is designed to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and uncover phenomena invisible to Hubble. One of JWST's key design features is its primary mirror, which spans a massive 6.5 meters in diameter, over twice the size of Hubble's mirror. This larger mirror allows JWST to collect significantly more light, enabling it to observe very faint and distant objects. Coated with a thin layer of gold to enhance its infrared reflectivity, the mirror is made up of 18 hexagonal segments that work together to create a highly sensitive observational platform. Another critical advancement is JWST's 5-layer sunshield, which keeps the telescope's instruments at a steady temperature of roughly -233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Each layer of the sunshield is made from a special material called Kapton, coated with aluminum to reflect sunlight. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, a stable position about 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to conduct continuous observations from L2. JWST's ability to focus on infrared light is particularly significant, as it enables astronomers to study redshifted objects, celestial bodies whose light has been stretched to longer wavelengths as the universe expands. Proxima B, a potential second Earth, has captivated scientists and the public alike as a potential second Earth located within its star's habitable zone. The planet has the right conditions to potentially support liquid water, a critical ingredient for life as we know it. With a mass around 1.1 times that of Earth, Proxima B is likely a rocky planet, similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from an identical twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual light while the other remains in eternal darkness. This creates an unusual environment with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, could offer a narrow strip of moderate conditions suitable for supporting life. The challenges posed by Proxima B's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its frequent solar flares, which release bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains any atmosphere, it would likely require a strong magnetic field to protect it from radiation. Without such protection, the surface environment would be hostile to life as we know it. Despite these challenges, scientists remain hopeful about the possibility of life on Proxima B. The planet's location in the habitable zone suggests that liquid water could exist, either on its surface or in subsurface reservoirs. Life could adapt to the extreme conditions, much like extremophiles on Earth, organisms that thrive in harsh environments, such as deep-sea hydrothermal vents or high radiation zones. These adaptations might include radiation resistance, subsurface habitats, or unique biochemical processes. The search for life is a scientific mission, and the quest for life on Proxima B is more than just a scientific undertaking. It is a journey to answer one of humanity's oldest questions: are we alone in the universe? Proxima B presents an intriguing opportunity, a rocky, Earth-like world that could possess the conditions necessary for life. As our technology advances, so too does our ability to explore this fascinating planet and uncover its mysteries. While Proxima B holds exciting prospects, its environment is heavily influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, which has a relatively stable activity cycle, red dwarfs like Proxima Centauri experience frequent and intense solar eruptions. These flares release bursts of X-rays and ultraviolet radiation, which can be powerful enough to strip away planetary atmospheres over time. For Proxima B, this means it faces continuous exposure to high-energy radiation, which could erode its atmosphere unless it has a strong magnetic field. On Earth, our magnetosphere protects us from harmful solar radiation by deflecting charged particles from the surface. If Proxima B lacks such protection, any atmosphere it might have had could have been stripped away long ago, leaving behind a barren, airless world. Even if Proxima B still holds an atmosphere, the regular radiation bursts could make it difficult for life to thrive on its surface. Any potential life forms would likely need to develop adaptations similar to Earth's extremophiles, organisms that survive in extreme environments such as deep-sea hydrothermal vents, acidic lakes, or high radiation zones like the Chernobyl exclusion zone. Could Proxima B ever have liquid water? Despite the challenges posed by solar flares, the possibility of liquid water on Proxima B remains an open question. Since the planet orbits within the habitable zone, temperatures could, in theory, allow liquid water on the surface, one of the key ingredients for life as we know it. However, its tidal locking complicates this situation. If one side of Proxima B is in eternal light and the other in constant darkness, extreme temperature differences could arise. The day side might be scorchingly hot, while the night side could be freezing cold. In such a scenario, liquid water could only exist along the Terminator line, the narrow zone where day meets night. This twilight region might offer moderate conditions, allowing water to exist in a stable state. Another possibility is that Proxima B has a subsurface ocean, like Europa or Enceladus, two of Jupiter and Saturn's moons. If the planet has underground reservoirs, they could be shielded from radiation and remain liquid beneath a protective ice layer. These advanced space missions hold the promise of dramatically reducing travel times to distant star systems, making exploration of Proxima B and other exoplanets more feasible in the future. Breakthrough Starshot, for instance, proposes to launch tiny, lightweight spacecraft equipped with light sails that would be propelled by powerful lasers, reaching speeds up to 20% of the speed of light. At that pace, a spacecraft could potentially arrive at Proxima Centauri in just over 20 years, providing an unprecedented opportunity to study the planet and its potential for life. As technological advancements continue, scientists are also working on other methods to gather more information about Proxima B, future missions may involve more powerful telescopes and space probes that could analyze the planet's atmosphere, surface composition, and climate in much greater detail. Instruments capable of directly imaging exoplanets and measuring the chemical signatures in their atmospheres could provide crucial insights into whether Proxima B could harbor life. The study of Proxima B and other exoplanets within habitable zones is part of the broader search for life beyond Earth. In recent years, the discovery of potentially habitable planets has grown exponentially, fueled by missions such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. As we discover more about these distant worlds, we are beginning to understand how common Earth-like planets may be and how likely it is that life exists elsewhere in the universe. Ultimately, Proxima B represents a unique opportunity to explore the possibilities of life beyond our solar system. Despite the challenges posed by its harsh environment and the unpredictability of its host star, Proxima B's location in the habitable zone and its potential to support liquid water make it one of the most exciting exoplanets to study. While it may be years or even decades before we can send a spacecraft to Proxima B, the knowledge we gain from future missions will undoubtedly shape our understanding of life in the universe and our place within it. In the meantime, astronomers and scientists will continue to rely on the power of space telescopes like JWST to study exoplanets and their host stars, improving our ability to detect distant worlds that could one day be our neighbors in the vast expanse of space. As we look toward the future, the exploration of Proxima B and similar exoplanets will remain a key priority in the search for life beyond Earth.